Hey, all you MRWC fans. This is Mr. Aynesworth, and we're going to get into a little retake review here on Section 2 in MRWC. And if you didn't complete your goals or reach your goals, if you didn't reach your goals on this test, meaning 80% or better, all right, go through this review, do all your notes or take all your notes in your spiral, all right, here. And I'm going to reference version 3 of the test. So this may not be your test, but I'm just going to reference it here to explain things and to get examples from. All right, but it's going to help you out nonetheless. Every class has 2 different versions, and the retake will have a different version. But we can reference this to get an idea of what's going on and what we need to do. And again, it's all about proper practice, doing the right thing. And so your best resource is your notebook, okay, where we do all our activities and everything. You got to go back there and actually practice problems that we've done. Your second best resource where we do all our examples is your spiral. Okay, we do all the additional examples there and use it to your advantage. Okay, practice what you learned 3 weeks ago, 4 weeks ago when we started this section. All right, now the test started off with a construction where you had to construct fractions like 1/5, 2/5, 3/5, 4/5. I'm not going to go over that here. All right, so let's just make a little note. Practice your constructions. All right, there are videos in Canvas. They're still available. Okay, so if you didn't get a 5 out of 5 on your constructions, well, go through the videos, all right? Go through them at your pace and practice, okay? I would say 90% of the people or more did an excellent job on their constructions. So the videos work, they're effective, and all you have to do is practice them and really pay attention and go through step by step, okay? All right, we're going to start here on this second page with the fractional techniques here. First thing I asked you guys to do is to find 3 rational numbers, okay, let's talk about rational form here too, between 2 fractions, okay, between 1/6 and 0.1 repeating. And the variations of the fraction does, obviously vary among the test versions, okay. One version had 1/6 and 0.1 repeating, another one had 1/7, whatever. It doesn't really matter, okay, but the idea is the same. So remember rational form. Okay, and that is an integer divided by another integer. Okay, it looks like A divided by B, where B is non-zero, okay, because you can't divide by 0. So I'm going to take a look at a different example here. Let's take a look at, let's take a look at 1/12 and 0.1 repeating. Okay, so let's say that we have 1/12 and 0.9 repeating. And we want to figure out some fractions in between there. So 0.1 repeating. We have to know what 0.1 repeating is as a fraction. And I saw a lot of people use one of the techniques to take a repeating decimal to a rational number, or to a fraction basically. And I saw this. So what we did here, and this was the second technique, is you let n equal 0.1 repeating, which is 0.1111 and so on. We multiplied both sides by 10, okay, and so I multiplied left n by 10, I get 10n. And remember, this is a repeating decimal, so if I multiply 0.1 repeating by 10, the decimal shifts right one place. Okay, just imagine 0.1 repeating is equal to 0.111111 forever, right? So if you multiply by 10, it just shifts the decimal one place. And so what you get here is 1.1 repeating, okay? So we get 1.1 repeating. By the way, make sure you put the repeating symbol on there, because if you don't, it's a totally different number, okay? So the little symbols matter. And when you subtract 10n minus 1n, all right, that's n is the same as 1n here, you get 9n, okay? Because 10 minus 1 is 9. And this repeating part here, okay, the repeating part cancel. So all you get on the right-hand side is your whole part, which is 1. Divide both sides by 9, and you get n equals 1/9, which is 0.1 repeating. And if you want to check that on Desmos, go ahead. That's a good idea. We do this all the time in class. You simply take any calculator of your choice, but online, the best calculator is this one. Okay, 1 divided by 9 is 0.1 repeating. See that? Boom. Okay, so once you're there, once you understand what 0.1 repeating is, which some people thought was 1/10. Okay, this is not 1/10, and that's what I was saying earlier. The repeating symbol makes a difference here. and let me emphasize that one more time. 0.1 repeating is not equal to 0.1. So if you take off the repeating symbol, you get 1/10. Okay, 0.1 repeating is 1/9. 0.1 is 1/10. So they're not equal, guys. And a lot of, there were a few people on the test that thought 0.1 repeating was 1/10, but that means they don't understand the symbol of the repeating symbol. Okay, so let's try to understand that better this time. The repeating decimal is not 1/10. All right, it's 1/9. Now that we know what it is, we got to find fractions or rational numbers between 1/9 and 1/12. So I'm going to line them up. I'm going to start off with a smaller one here, 1/12, and then we'll figure out what fractions we have between these two. There's different ways to do this. Okay, so I'll approach different ways here. So one way is to just look at simply the denominators. Okay, so what we could do is I can find numbers between 9 and 12, and that obviously is 10 and 11, right? So 1/11 is between there, and then 1/10 is between there. And there aren't any whole numbers between 9 and 10, so let's use a few decimals. So how about 9.5? Okay, so there we go. There's 3 rational numbers between the two fractions. However, 1 divided by 9.5 is not a rational form because 9.5 is not an integer. So all you do is multiply it by 10/10. All right, and you get 10 divided by 995, and then you have to reduce that, divide by 5, and you get 95 divided by 5. Let me see, what would that be? So 95 divided by 5 divides in 4 times, so it's 19, so 2/19. Or you could have done this. This is another slick way to do it. You could have just multiplied by 2 in the form of 1, so 2 halves, and you get 2/19. 2 times 9.5 is 19. So my 3 rational numbers are 1/10, 1/11, and 2/19. Okay? Now the other way to do it is using LCD, going back to very basics. So method number 2, if you don't like this one, this is method 1. Okay, using decimals. Okay. So using decimals, I use a decimal there, 9.5. That's method 1. Method 2 is the LCD, going back to basics. All right, the LCD of 12 and 9 is 36. So let's try that. So 1/12 times 3/3 equals 3/36, and then 1/9 times 4/4 equals 4/36. But in this case, the numerator is 3 and 4. There aren't very many whole numbers between those two, so you're going to have to use decimals again. So I saw a few people get really creative here. So instead of using 3/3 and 4/4, these are called forms of 1 right here. They actually increased it. They used 9 and 12. So I'm going to redo this here to show you what other people did. So 1/12 times 9/9. Okay, 9 times 12, that's 90 and 18, that's 108. So you get 9 out of 108, and then 1/9 times 12/12. Again, I'm just using techniques from 5th grade, guys. It's called the LCD. So, and that's equal to 12 108ths. Okay, and so now if you want to figure out some fractions between them, you might be able to. Okay, there we go. So 12 out of 108. So what's between 9 and 12? How about 10 108ths? How about 11 108ths? And then between 11 and 12, there aren't any more whole numbers, so you have to use fractions here. So how about 11, actually, instead of 11.5, let's go 11.1, just for funsies here. All right, because you can pick any decimal between 11 and 12, and you get this. And then when you convert it to a rational number, all right, you simply multiply it by 10/10 to shift the decimal, because that's all 10 multiplying by 10 does, and you get 111 divided by 1080. And if you wanted to, you can simplify this actually. So you can divide both by 3 and simplify it if you like. So 111, divided by 3. If you want to use your calculator, that's fine, but this divides in 3 times here. Remainder 2, 3 and the 21 is 7, so it's 37. And then you take 1080 divided by 3, divides in 3 times, divides in 18 6 times, divides into 0 0 times, so 360. So here we have three rational numbers as well: 10 108ths, which can be simplified, 11 108ths, and 37 360ths. Top, we have different fractions, but another possibility here, because again, these problems have like an infinite number of possibilities, guys. 1 11th, 1 10th, and 2 19ths. Okay. All right. So that's the first part here. The second part, number 5, how many rational numbers are between two rationals, or how many numbers are between two rationals? Well, between any two numbers on the number line, there's an infinite number of numbers. And we talked about that in class. Like, I can continue doing this. I can pick any two of these numbers, like, for example, these two right here, 1 12th and 1 11th, and I can find three rationals between those. And I can continue doing this process forever. And so it kind of gave everybody the idea that between any two numbers, there's an infinite number of numbers. Okay. Number 6, I already talked about, rational form. That's that is, well, just integer of an integer. I went over that a billion times. Now, number 7, I think the best way to do number 7 is going back to basics. The people that did really well in this problem used the LCD technique here. And when they did that, they did really well. If you use decimals, using decimals in the denominator here, like 11.5, some people thought 5 divided by 11.5 was halfway, but the decimal technique does not work for getting the average or the middle number. So this is not effective. You can check that with the calculator if you like. So the best way to do it is get an LCD or simply get an average, which is just adding them up and dividing by 2. An average is the sum divided by 2 when you're averaging two numbers. And that's what I did up here on this example. So let's go through one. Let me pick a different one to exemplify this. So I'm going to pick two different fractions here. So this is number 7. Okay, when you want to find a number exactly halfway, you want to find the middle number. So find the middle number, all right, between two fractions. And I'll just make up a couple fractions here because this was someone's test here, so I want to do something different. All right, so find the middle number between, let's say, 3 sevenths and 3/8. Let's do that. Okay. Now, again, this is the middle number. We're talking a middle number. We're talking about an average. Okay. The average always gives you a middle number here. But the easiest way to do it, and probably the best way to visualize it and understand it, is using the LCD technique. All right. So I'm going to use to find the LCD. I'm going to get common denominators here, draw it on a number line to see if it makes sense to you guys. All right, so here we go. So let's do our homework first. So 3 sevenths here first. I'm going to multiply it by the other denominator, 8/8. I get 24/56. I'm going to work on the other one now. I'm going to multiply 3/8 by 7 sevenths to get a common denominator. So this is going to give us 21/56. So notice that they both have a common denominator. So this method here that I'm showing is using the LCD, not decimals. And I think this will probably make more sense to everybody because the decimal technique was new. But unfortunately, the decimal technique in the denominator does not work for finding the average. It does work in the numerator, but not in the denominator. Okay, so now what we want to do is just kind of draw a simple figure here, or draw some number line, excuse me. Okay, so there we go. So let's suppose that this is 21/56 here, and let's suppose that this is 24/56 here. All right, and the middle number, all right, exactly halfway is called the middle number. If you read number 7 up here, exactly halfway. Okay, guys, that's the middle number. Happens to be here. What would that be? Okay, well, let me see. You just have to focus in on the numerators, and there's a couple different ways to think about this. You got to find the halfway point between 21 and 24. So you can look at it as a fraction if you want, but just simply speaking here, we got to find, let me just simplify this a little bit. If this was the number line, if this is 21 and this is 24, you got to find the middle here. You know, what would this be? Well, there's 3 units between these two numbers here. Between 21 and 24 is 3 units. And if you take half of 3, okay, half of 3, well, that is 3 halves, okay, or 1.5. And what we want to do is shift over 1.5 units from 21. That'd be 22.5, okay? So if you shift over 1.5 units plus 1.5, you get 22.5, okay? That's in the middle of these two numbers, 21 and 24. 22.5 is 1.5 units from 21, and it's 1.5 units from 24. So up here, this is 22.5, 56 out of 56. But then again, you got to finish the problem here, and you got to make it rational, because it says find a rational number. All right, so we're going to take this, and we're going to take 22.5 out of 56. You simply multiply it by maybe either 10 tenths or 2 halves. 2 halves, I think, would work. You don't have to multiply by 10 every time. 22.5 times 2, that's 44 and 1, 45. You can check that with a calculator if you like. Divided by 112. All right, and there's your middle number. Okay, that's probably going to be the easiest way to do it, using the LCD and go for it. Or you could take the average. So I'm going to just finish off with method 2 here. So using averaging, you take the sum divided by 2, or you just take half the sum. Sum means you simply add them. And I say half the sum because we're dealing with fractions here. So when we take 3/7 plus 3/8, watch what happens. Okay, so right here I take a half of the sum, and we use the 3 product rule. 3 times 7 is 24, plus 7 times 3 is 21, divided by 7 times 8, which is 56. And then 24 and 21, well, that's 45, right? 45 out of 56. And when you multiply the fractions, 1 times 45 is 45. 2 times 56 is 108. No, excuse me, not 108. What am I saying? 112. 112. 2 times 6 is 12, guys. Sorry. And notice we get the same answers here. Okay, this answer is the same as the previous one. Okay. So method 1, what I did to find the middle number is I used the LCD. Okay, so this is method 1. Method 2 is averaging. And you just got to find what makes more sense to you. And again, going through this video is one thing. Watching it, getting good is another thing. So what you need to do is practice this same problem. Practice this, 3 to 5 times to master it. Practice the same problem. This same problem. All right, 3 to 5 times, all right, to master. I used to do this all the time in college, all right? I used to take the hardest problems my instructor gave me, and I went to the university on the big whiteboards, and I used to redo the problems until I can do it easily. And that's exactly what you guys should do. Take this problem, solve this problem using both methods here as many times as it takes until it becomes easy to you. And then when you come to the test, the fractions are going to be different, but the method's going to be the same. All right, so you got to get good at both method and the arithmetic. Okay. Now let's finish up here. It says number 7, part B. It says less than halfway between the two fractions. So we already did the work here. So a number less than halfway. Okay, so this number here, this is exactly halfway, right? Because it's in the middle, right? Exactly halfway. All right. Less than halfway is to the left of it. All right. Less than halfway. Just pick a number between 21 and 22.5, like 22. Okay, so less than halfway would be 22 out of 56. And you just got the other answer. Okay, and there's a lot of choices here. You could have picked 21.5 out of 56 and then converted it. So there's a lot of answers possible there because there's an infinite number of fractions between any two fractions. All right, so as long as you pick a number less than halfway, and make sure, by the way, that the smaller number is on the left. It goes small to big on the number line. Okay, some of you guys reversed that and got the problem wrong. So take a look at that. Make sure you have the smaller number on the left and the bigger number on the right on the number line when you draw it, because that wasn't the case for some of you guys on your test. All right, let's see what else we have here. So then we get into number 8. What's rational, what's not. Okay, so one of the problems was log base 6 of not 32 but 36. Okay, and that was equal to 2, and that's rational. Okay, so another one could be log base 5 of 25. All right, now to think about that, you got to be taking the base here, which is 5, and 5 to what power gives you 25? You got to be thinking about that, and since 5 squared gives you 25, this log is equal to 2. If I take, I'm just going to make some up here, and you write it down in your spiral too, by the way. I'm just talking about concepts here. Log base 3 of 27. Well, what would that be? Well, I know that 3 to the first is 3. I know that 3 squared is 9, so the answer is not 2. Okay, because again, these logs are actually exponents of an exponential. Okay, I know that 3 to the third, all right, is 27. So you got to know your powers of a number here. So this answer is 3. The log base 3 of 27 is 3. And because of that, it's an element of the rationals, Q. So it's rational. Okay, I varied the log up on everybody's test. Everybody has a different log, but the idea is the same. It's the exponential. Okay. Now, this one, part B, you have to know how to deal with negative exponents. This one was 10 to the negative 2, which if you convert it to a fraction, it becomes 1 over 10 squared. 10 squared is 100, so you get 1/100th, which is rational. Let me take something similar down here. If you have, let's say, 5 to the negative 2 power, that's 1 over 5 squared. You got to use the negative exponent rule from Algebra 1. You convert it to a fraction, right? And then you simplify, you get 1/25th, and that's rational. Remember, Q stands for rational set. If you have, I'm just making up some new ones here, 3 to the negative 2 power, that is 1 divided by 3 squared, which is 1/9, and that's rational. If you add 4 to the negative 2, that's 1 over 4 squared, which is 1/16th, and that's rational. So you have to use what's called the negative exponent rule. Negative exponent rule that you guys learned in Algebra 1 a couple years ago. And you have to know how to deal with that. Okay? Do not use a calculator. Some of you guys did, and you're not supposed to use calculators here. So if you type in 3 to the power of negative 2, right here, notice that it gives you 0.1 repeating, and then as a fraction, it's 1/9. Okay? But you wrote down the decimal here, and you're not supposed to use a calculator. You're supposed to know what you're doing. All right, so you're supposed to take the concepts from the past, like in Algebra 1, and apply it to the present. Okay, because you guys are in a pre-calculus class as seniors here. Okay, and then I gave versions of pi to a power. Now, pi is the most famous irrational on the planet. Okay, that and E. Okay, Euler's constant. So write this down. Pi is the most famous irrational number. So pi, any form of pi cubed, pi squared, pi, just flat out pi. I don't care what version of pi you got. It's irrational, guys. It's not a rational number. You cannot write that as an integer over an integer. And likewise, the square root of a prime number, okay, 7's prime. The square root of a prime is always rational. Write that down in your notes. The square root of a non-square is always rational. I've talked about these things, but you just got to practice and study in such a way that you guys retain this and understand it, okay? You cannot write the square root of 7 as an integer over an integer or as a fraction. You just can't do it. It's a non-terminating, non-repeating decimal. All of these are. Okay, irrational numbers are non-terminating, and non-repeating. So you can't convert them to a rational number. Make sure I'm writing over a previous version of the test here, but I want you guys to actually write this down in your spiral. So if you haven't done so, pause the video right now and get all that down, because these are the things that you need to know. Okay, so let's go to the last page here. Okay. So use prime factorization to determine the fractions repeat or terminate. If terminating, determine the number of digits. If repeating, explain why. Okay. So you guys have to remember how to factor. Okay, so notice that I take the denominators here, like 160, and I factor it. That was pretty well done on the test, actually. You guys did a good job on that. If the factors of the denominator are only 2 and 5, it's going to terminate. If you have other factors other than 2 and 5, like 3 or 7, or anything other than 2 and 5, it's going to repeat. Okay? So what we want to do is factor the number and look at its prime factorization. Okay? No calculator here. No calculator. Write that down. You don't need a calculator for this entire test. The only thing I use it for is to check and to get you guys to understand what you're doing here. I mean, I could take 3 divided by 160 and show you that it terminates. So 3 divided by 360, but 160. Okay, and notice that it terminates after 5 digits. Just count them up. 1, 2, 3, 4, 5. It terminates after 5 digits. But why? Well, the reason why is because 2 to the 5th power times 5, the only factors, look right here, these are the factors right here on the right. Okay, the only factors are 2 and 5. And there's 1, 2, 3, 4, 5 factors of 2 to the 5th power. So you look at the exponent, and that tells you the number of digits it terminates on. So it terminates after 5 digits because of the power, not because of the other 5, because of the exponent. So you guys were supposed to be looking at the exponents on this one. So let's do another one just for funsies here. Let's take this problem here, and let's come down here. Again, you're doing all this in your spiral. So let's suppose we take, I don't know, I'm just going to make up a number, 1/80th. Okay, I'm just making this stuff up. So I'm going to take 80 and factor it. So 80 divided, and by the way, these should be prime factors. Okay, you always start off with prime factors. Prime factorization. So I don't start off with 4, 80 is divisible by 4. I don't start off with 4 because 4 is not prime. I start off with 2. So 80 divided by 2 is 40, divided by 2 is 20, and divided by 2 is 10, divided by 2 is 5. And 5 is prime, so you can only divide it by itself. So right here, that's 2 to the 4th, right? There's 1, 2, 3, 4 2's being multiplied together. So the factors of this are 2 to the 4th and 5. So I rewrite it. 1/80th is equal to 1 divided by 2 to the 4th times 5. And a lot of you guys didn't write this correctly either. You write it as a fraction. It's 1/80th, not 80. Okay, and because of the 4 here, the 4 right there, it terminates, the only factors are 2 and 5, so it terminates. Now, I know it terminates after 4 digits because I'm looking at the exponent. That's the key. So it terminates after 4 digits, and I can prove it to you. Okay, let's divide 1 by 80. So take 1 divided by 80. All right, and notice it terminates after 4 digits. Just count them up. 1, 2, 3, 4 digits. Okay, now that doesn't always happen, so let's take something like this. Let's take, I don't know, so 5/54, let's say. Okay, and let's work on this one. Okay, so let's take 54 and factor. So 54 divided by 2 is 27, divided by 3 is 9, divided by 3 is 3, divided by 3 is 1. So now I have, right here, I have 3 to the 3rd power times 2. So my factors are 2 times 3 to the 3rd, 2 times 3 to the 3rd. So when I re-express this, so I've got 5 divided by 3 to the 3rd, because there's 3 3's here, 3 to the 3rd power times 2. So now I notice there's factors of 3, and because of this guy right here, this makes it repeat. If you have any other factors other than 2 and 5, it's going to repeat. So I look at this, and I know it repeats. It repeats because of the 3. And it's called a factor, so the factor of 3. So get used to learning how to explain your thoughts, explain your reasoning. If you have only factors of 2 and 5, it's going to terminate after some point. If you have factors other than 2 and 5, like 3, 7, 11, anything other than 2 and 5, it's going to repeat. I can prove that to you too. You just take 5 divided by 54. Boom. And notice it repeats. Okay, look at that. So it goes 925.0, 925, 95, 95, 95. It repeats. Boom. Okay. So let's get back to the test here. Let's see, what other parts do we need to get to? So that's number 9. Okay. So this is all number 9. Again, all of this work right here that I'm talking about here is all in your spiral. Okay. Now, number 10. So how do you show how to convert a fraction, a rational number, to a decimal? All right, using base 10 fractions. Okay, no calculator here. Some people use a calculator. You're not supposed to use one. I didn't need one. Okay, so let's go through this. So I'm going to take number 10, all of this right here. I'm going to come over here. Number 10. So how do you use base 10 fractions? So I'm going to explain the 7/40ths again. So you need to factor it first. So that's the first thing you do. So 40 divided by 2 is 20, divided by 2 is 10, divided by 2 is 5, divided by 5 is 1. So this is equal to 7, and this part right here, that's 2 to the third power. So 2 to the third power times 5. Now let's go back to the problem here. It says using base 10 fractions. Okay, base 10 fractions are where the denominator is the power of 10. Okay, power of 10. What does that mean? I'm talking about 10, 100, 1,000, okay, 10,000, okay, and so on. Powers of 10. So I need the denominator either 10, 100, okay, in fact, let me write that out. Okay, powers of 10. Let's make sure you guys understand that. 10 to the first is 10. That's 10 squared is 100. 10 cubed is 1,000. 10 to the fourth is 10,000. These are called powers of 10. All right, but the denominator is 40, not one of these numbers here. So how do you convert it to that? Well, what you want is to rewrite both the factors 2 and 5 to have the same exponent. So I noticed that 2 already has an exponent, and the exponent is 3. So it'd be really nice to have 5 to the power of 3 here. And it's not, it's 5 to the first power. So what I need is 2 more 5s to get 5 to the third power. I need 5 to the third, I only have 5. So I just multiply it by 5 squared over 5 squared. It's called a form of 1. Okay? So what do we get? So notice the progression here. I put some symbols in. I put the equal signs in. I put the time symbol in. I'm multiplying here. So I got 7 times 5 squared, which is 7 times 25. 5 squared is 25. Divided by 2 to the third times, and this right here, this is 5 to the third, all right? 2 to the third times 5 to the third. Well, we just kick in a little of algebra here, guys. The denominator, when the powers are the same, all right? When the powers are the same, you can rewrite it as 2 times 5 to the third power. This is, it's an exponent law in Algebra 1. Okay, this is an exponent law, all right, from Algebra 1. And all this stuff is Algebra 1 based, if you figure it out, okay? So if you're really good at Algebra 1, you could do all this very easily. If you're weak in the Algebra 1 work, well, then this is going to be extremely difficult. All right, but everything comes from Algebra 1. So when the powers are the same here, and they're both 3, you can rewrite it. And the reason why is because now I have 10 to the third power, which is called a power of 10. All right. So now 7 times 125, 7 times 25, think 7 quarters, okay, 175. Okay, so just multiply up there. And then I have 175 divided by 10 cubed. And this is 175 divided by 1,000. Okay, notice down here it's a power of 10. Okay, 10 cubed is 1,000. And because of that, my friends, guess what? Don't need a calculator here, do I? Because when you divide a number by 1,000, you shift decimal left 3 places. Shift decimal left 3 places. And this is grade school stuff. Okay, you should know that. So this is 0.175. And I can prove that to you. So here we go. So 7 divided by 40. So 7 divided by 40. Boom, 0.175. Okay, so we use the calculator to check, but we do not use the calculator to compute. Okay, I'm going to write that down. So use the calculator to check only. Okay, not to compute. Write this down, not to compute. A lot of people used it incorrectly, and you didn't get the credit because you didn't know what you were doing. Notice I didn't use a calculator above here in all my calculations. And again, this is one of these things right here that you need to practice multiple times to master. So take 7/40ths to get a blank piece of paper here, take the original problem, 7/40ths, and go through the 1, 2, 3, let me see, 1, 2, 3, 4, 5, 6 steps. This is 6 steps. Practice, okay? Practice the 6 steps. And then go into your spiral. We did a lot of these in the beginning, but we did it like 3 weeks ago. All right, so go into your spiral, grab one that you already have a good solution for that you know is correct, and practice. The key is practicing. Okay, so in fact, let's write that out. Perfect practice makes perfect. Perfect, not just any practice, guys. Perfect practice, all right, makes perfect. But you got to do a lot of it. Okay, practice doesn't make perfect. All right, perfect practice makes perfect. So you have to really do the right thing. You got to practice things perfectly and really, really well in order to get from, obviously from 7/40ths to 0.175 without a calculator. All right, no calc, okay? No calc needed here. All right, you didn't see me use it. I just checked it. All right, and again, make sure all this goes in your spiral here. Write down all the key steps here, because when you present it to me, I'm going to be looking for all this. All right, I want to know that you actually practiced and you went through this and you got better, because there's no reason to retest here, guys, unless you do the right thing. All right, correct your work, practice, come prepared. All right, we only need to do a few more here. So number 11. Okay, use the sum of an infinite geometric series. That's what you see right here. All right, using the sum of an infinite geometric series, convert a repeating decimal, all right, to a rational number. All right, so let's take that down here. So let's, instead of this fraction here, let's take another fraction. All right, so let's take 0.038 repeating. So first of all, let's expand it. So 0.3838383838 and dot dot dot. This is an infinite repeating decimal. Okay, so here we go. So I expand it just like if you look at number 11 here, I expand it first. Okay, this is called expanding. All right, and then I decompose it. All these steps, they're in your spiral because this is how I taught it. Decompose it. So you take it, look at its parts. So the decomposition looks like this. 0.38 is my first part. My second part is the second or the third and fourth digits. All right, so 0.0038. And so notice they're in the third and fourth position, so you got to have 2 zeros as the placeholders. The third portion here is 0.0000, so 4 zeros, 38, plus 0.000038, and then it goes on, so put plus dot dot dot. And again, without the dot dot dot, without that infinite part, okay, it's not technically correct. This is an infinite repeating decimal. And so the plus dot 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 is important because it doesn't stop, you guys. All right, now we convert to fractional form. So right here, to go from a decimal to a fraction, that's called converting to fractional form. Fractional form. So here we go. So 0.38 is 38 hundredths. This is 38, let me see, thousands, 10 thousandths. And so there's 4 digits, so there's going to be 4 zeros. And then this is going to be tenths, hundreds, thousands, 10 thousandths, 100 thousandths, millions. So this is 38 millionths, and that's going to have 6 zeros. 246 plus dot dot dot. So you got to go to fractional form. And then you have to understand a few other things. So let's get back to our example here. So this is our first term, A1. So A1 is equal to 38/100ths. Don't reduce it, okay? Don't simplify it. Just leave it like that. There's a reason why. It makes it easier for you, okay? So just leave it as 38/100ths. The common ratio that you multiply the fractions by to get to the next fraction here, in this case, you go from 100 to 10,000, so you're going to have to multiply by 1/100th. Okay, that's called a common ratio, so that's R, 1/100th. You got to be thinking, what do you multiply 100 by to get 10,000? And it's not 10, okay? It's actually 100, so, but these are fractions here, so you have to multiply by 1/100th, not just 100. Okay, it's called a common ratio. It's a fancy word for just the number you multiply the first fraction by to get to the next fraction. Okay, so that's called a common ratio. Okay, and then you have to know how to sum up an infinite number of terms. And so we use S for sum, and it's always equal to A1. It's A1, first term, divided by 1 minus R. This stands for sum, S stands for sum. And then you substitute your numbers in. So here we go. So 38/100ths divided by 1 minus 1/100th. And notice I'm using an equal sign here. And a lot of you guys got to put in the punctuation, guys. You got to put in the equal signs, the time symbols, and make it look good. All right? It's kind of like being in an English class, but you're in a math class here. You got to put in the proper symbols to make sense of it. So this plus dot dot dot, those are important symbols. All right? The equal sign is an important symbol, because it means that things are equal. All right, so here we go. So let's finish up. So 38/100ths divided by. Now here, if I had a pizza, 1 minus 100th, if I had one pizza right here, so let's represent this as a pizza, and I took it and I divided it into 100 pieces, and I took one out of 100, I subtract 1 out of 100, I would have 99 slices left out of the original 100. So think pizza here, guys. 1 minus 1 out of 100 is 99 out of 100. It's that simple. And at this point, you want to multiply by the reciprocal. So from here to here, you multiply by the reciprocal of the denominator. So I take 38/100ths multiplied by 199ths. Okay, the reciprocal of the denominator right there. So again, you have to understand what reciprocal means, which is just the fraction inverted. So if you invert or switch the numerator and denominator of 99/100ths, you get 199ths. All right, simplify a little bit. 100 divided by 100 is 1, and then you are finished, my friends. And that's equal to 38 times 1 is 38. 1 times 99 is 99. And you get 38/99ths. And if you want to, I'll prove that to you. So you take 38 divided by 99, and voila, you get 0.38 repeating. Okay, and again, this is an example right here that if you just take this one example and you practice, okay, you practice 5 to 10 times. Okay, I was going to say 3 to 5, but I would say for you guys, 5 to 10 times. 5 to 10 times, all right, to master it. Why? Because you got to get the process down, all right? And if you don't practice, you're going to struggle on the retake. If you practice and do the right thing, you're going to do much better, trust me. So you got to trust me, guys, that I'm giving you good information here, that I'm giving you good advice in terms of how to practice and how to get better, okay? So, and again, we have a lot of these problems in our spiral. So you take something that you've done, like this right here with me, all step by step, and you practice to make perfect. All right, and the last one here is your proof. Okay, so here in this one, number 12, the set of positive reals closed. Actually, I changed this one on the test right here. I had you guys take a rational number and just either square or prove that it's closed under squaring or cubing. Okay, so I'm going to change the proof. So ours was different, okay? So I'm going to state the problem that you guys had. So prove that a rational number, or the set of rationals that the set, and this goes in your spiral here, so this is similar to number 12. Okay, sim to number 12. The set of rationals, okay, not integers, but rationals. I'm talking a over b now, okay, where b is not equal to 0. That's the set of rationals, or q. Okay, the set of rationals are closed under, let me see, one test was squaring, so I'll do that one first. Okay, under squaring. And I say prove, because it is true. A rational squared is always a rational. Okay? So if I say prove that it's closed, that means it's true. So the idea is that a rational squared, here's the idea, okay, is that if you take any rational number, all right, square it, it's always rational. That's how simple it is. All right? Now, we talked about proofs with adding, subtracting, multiplying, dividing, but guess what? There's other operations like squaring, cubing, taking something to the fourth power. It doesn't really matter. There's many different ideas. All right, so here we go. Let's state the proof. Okay, so you let n is equal to a over b, all right, where b is non-zero. You don't need two fractions, guys. You just take a fraction, a rational number, all right, and then you square it and make sure it is rational. All right, so here we go. So you take a over b, you square it. Well, that's a over b times a over b. Well, that's a times a divided by b times b. And remember, a, whoops, I gotta say this, a and b, okay, are integers. Okay, some of you guys like using symbols. A and b are elements of, not q, but z, all right, because they're integers. So you got to specify what type of numbers a and b are. So that's part of the proof right there. And then what does that tell me? Well, this is an integer times another integer in the numerator. B and both, b is an integer, so this is an integer times an integer. And we also know that an integer times an integer is just an integer. That's something that we learned in the very beginning of section 1, in the very beginning of school. Okay, so you have to rely upon what you know. Okay, you know that, okay, an integer times an integer equals an integer. You also know that an integer, all right, plus an integer is an integer. You know a lot of things that you can assume. Well, you have to use some of those facts. And guess what? This is rational form right here. It's an element of the set of rationals. This is called rational form, and which is the correct form. We wanted to show that a rational squared is always rational. So we took a rational number like a over b, we squared it, we got another rational, and so therefore, boom, all right, it's closed under squaring. Okay, so this tells me right here, okay, that rationals, here's the conclusion, are closed under squaring. So you got to state your conclusion. It's called a conclusion under squaring. And this is, again, I keep talking about study methods here, okay? You take this proof, no matter how simple it is, okay, and you write it out, and you practice this 5 to 10 times, all right? So the key idea, all right, is practice. Practice this, write it out, because listening to me is one thing. Doing it on your own is another thing. Okay, I make it look easy because I have 30 years of teaching experience. All right, but you don't. So practice this 5 to 10 times, all right, to master. And again, if you do that, you will come in well prepared. If you don't, you may not even pass the retake. So you guys really have to do the right thing. All right, now the other proof was cubing, and the cubing one is almost the same idea. So I'm going to do it off to the side. So here's the alternate version here. So prove that the set of rationals are closed under cubing, which is just raising it to the third power. So one version had squaring, the other version had cubing, and some people actually got it. All right, so you start off the same way. Here you take the assumption that we're working with rationals, not integers. Okay, so we just start with this here. Boom. Okay, so you start off with a and b being a, a over b being a rational number, and then you go for it. So here we go. So this time I'm going to cube it, so raise it to the third power. And by the way, put in parentheses around a over b. Some of you guys wrote it like this, okay? And if you do it like that, you're only cubing a and not the fraction a over b. So this is incorrect. Make sure you put parentheses. So a over b times a over b times a over b, oops, a over b. That's what cubing means. It's the same as a times a times a divided by b times b times b. And again, here we go again, an integer times an integer times an integer divided by an integer times an integer times an integer gives you an integer divided by an integer, all right, which is rational form, and therefore it's closed under cubing. Okay, because that is an element of the rationals. This is what rational form is all about. So you say, okay, here's your conclusion again. So the rationals, okay, are closed under cubing. So make sure you write down the conclusion that I put out there in red on both proofs. So that's both proofs on both tests, or all the tests. And again, on your retake, it'll probably be just something different, right? But if you understand the idea, all right, and you practice, all right, you'll be able to adapt and go with the flow here. You just have to know what to do, all right? Some people didn't even know how to start. If I tell you that you're going to start with rationals, you start with a over b. If it's an integer or an even integer, then you start with 2k. If I say start with an odd integer, you start with 2k plus 1. But in this one, we're dealing with rationals. In section 2 is all rational, so we start off with a over b. All right, and my friends, that is everything right there. There's the test. All you guys need to do is actually practice, okay? I went through a lot of concepts here. Should have all been in your spiral. All right, like I said in the very beginning, make sure you practice your constructions here. This is for the retake on Chapter 2 for Section 2 test at MRWC. All right, MRWC. I'm Mr. Aynesworth here. All right, practice makes perfect, so make yourself proud. Talk to you later.